some of the most important properties of logarithms are called the logarithm laws. And basically, if you have multiple logarithms, you can put them together into one logarithm, or you can take one logarithm and split it apart into multiple logarithms. And that's what we're going to look at here. We're going to look at how these relate to the exponent laws that you should already be familiar with, and then do some practice with both. So let's recall these exponent laws first. So we're going to look at three of them. If I've got x to the m power times x to the n power, well, I've got mx's multiplied, I've got nx's multiplied. So altogether, I've got m plus n x's multiplied. So this operation on the left is multiplication, while the operation on the right is addition. So we've got a relationship here between multiplication and addition. Similarly, if I have x to the m divided by x to the n, well, n x's would cancel from m total x's, leaving me m minus n x's altogether. And so this relates division to subtraction. And the reason I'm drawing a double arrow is because the left side is multiplication, the right side is addition, but I could also start with the right side and go to the left side and change addition to multiplication. The last property is if I take x to the m power and raise that to the n power, well, I've got mx's multiplied and I've got n copies of that. So that gives me m times n x's all multiplied together. So this guy's a little bit different. The left side, we have an exponent, which on the right side turns into multiplication. So we get these relationships of operations: multiplication and addition, division and subtraction, exponentiation, and multiplication. We're going to see the same thing is true with the logarithm laws. So I'll write those here. So these are new, and the logarithm laws look like this. We're not going to prove these, but I'm appealing to your intuition with the exponent laws. If this were a more advanced class where we're interested in proofs, I probably would prove these. So let's look at log base b of x times y. So the argument here has multiplication. Well, what this is going to do is this single log is going to break apart into two logs, log base b of x and log base b of y, but the multiplication turns into addition. So we get this relationship again in terms of logarithms. So notice that going this way is, if I start with the one log and break it apart, this is the expand direction, okay? If I go the other way, it's the combine direction. And I'll write that after I get all three laws written. Similarly, if I have log base b of x divided by y, well, this division is going to turn into subtraction when we break the log apart to be log base b of x minus log base b of y. And lastly, if I have log base b of x to an exponent c, so x to the c power, well, this turns into multiplication. This is a little bit different than the other two. This does not result in two logs. We still have one log, but this exponent c turns into multiplication by the log. So it turns into a coefficient. That's why I'm using c. So we get c times log base b of just x. So lots of times what we kind of do to think about this is this exponent can sort of jump back and forth, either inside the argument as an exponent or outside of the log as a coefficient. So these log laws could be gone from left to right in the expand direction, where you take an operation and expand it, or you could start on the right side and put everything together and go to the left side and use the combine direction. Now, a handy tool for remembering these laws, let me move this over a little bit, is to think about your order of operations. Your order of operations. So, you know, this is your PEMDAS parentheses, and then exponents, multiplication, division, addition, subtraction. Well, we don't have to worry about the parentheses. That's not part of the operations we're looking at here. So I'm going to start with E for exponentiation, and then we do multiplication, division, and then we do addition, subtraction. And one of the really cool properties of logarithms is that they change our operations. It's one of the reasons that they were discovered. And so if we're working in the expand direction, you can see that we start with a complex operation like multiplication, and it simplifies to be, or becomes more simple to addition. Division turns into subtraction, which is more simple. Exponentiation turns into multiplication, which is more simple. So if we want to expand, we're moving down in order of complexity. So exponentiation turns into multiplication, multiplication to addition, division to subtraction. Now, if we go the other way, we're starting with a more simple operation like multiplication, subtraction, or addition, and changing it to exponentiation, division, and multiplication. So if I want to combine logs, then my operation gets more complex. And so we go in the opposite direction. Subtraction becomes division, addition becomes multiplication, and multiplication becomes exponentiation. So I kind of like to use this order of operations ladder to help me keep track of what happens here. Now there's notation as well. That's where most students mess up. I think this part's pretty easy to catch on to, this ladder of operations. But understanding that when you expand multiplication or division, it turns into 2 logs with addition and subtraction. And when you combine, 2 logs turn into 1 log. So when I grade logarithm law work, I'm looking for proper notation and used in the laws properly, not just getting the right answer. So let's do some examples so I can show you how to write these. So let's do some combine into a single log examples. Number 1, let's look at 1/2 times the log of x plus 2. And remember, log is base 10 if we don't write a base, minus 3 times log of x. I don't need parentheses around the argument x because there's not addition or subtraction, so I can leave it like that. If you like the parentheses, which is what I liked as a student learning this for the first time, put parentheses around the x. Plus 4 log of z. And same thing on the z here. And we want to combine these into a single log. I'm going to go one step at a time here. And I can't deal with the subtractions or additions because right now my logs have coefficients. And my addition and subtraction laws only work if I've got log plus log or log minus log. So I've got to deal with those coefficients first. So I'm going to use this last law to take the coefficients and turn them into exponents. So the 1/2 is going to turn into an exponent on the argument x plus 2. 3 is going to turn into an exponent on the argument x. And 4 is going to turn into an argument or an exponent on the argument z. So what I get is log of x plus 2 to the 1/2 power minus log of x to the 3rd power plus log of z to the 4th power. Okay? And now we have additions and subtractions of just logs with no coefficients. So I can start combining these. Now, you can also, because it's addition and subtraction, you can rearrange these terms however you want. You could do log of x plus 2 to the 1/2 plus log of z to the 4th minus log of x cubed if you want to do that order. But I'm going to leave it like it is. And I can only combine 2 logs according to my law. So I'm going to combine the first 2 logs first. When I combine them, they turn into a single log. And when I have 2 logs subtracted, when I combine them, I get division of the arguments. Well, one thing I'll mention is that x plus 2 to the 1/2 is the same thing as the square root of x plus 2. So on top I have the square root of x plus 2. And because I'm subtracting log of x cubed, I need to divide by x cubed. Notice that this is a single log. I don't have a log of the top and a log of the bottom. That's where most students mess up. And then I'm just going to carry down my next log, log of z to the 4th. Now I've got two logs, I can combine these. So when I combine these logs, I get a single log, and it's addition, so I'm going to multiply this argument, the first argument, by the second argument. So when I do that, when I multiply a fraction by z to the 4th, z to the 4th just goes on top. So I'll write z to the 4th times the square root of x plus 2 all over x cubed. And now we've combined this completely into a single log. I think combining is a little bit easier than expanding. And I'm doing some pretty pretty thorough examples here to show you that even complex problems can be worked through one simple step at a time. Example 2, log base 3 of x plus 1 minus left bracket log base 3 of 2 plus log base 3 of 4 minus 2 log base 3 of x plus 2. Close your right bracket. What I'm going to do is go ahead and distribute this negative to get rid of the brackets. So all my logs are free to start combining. And instead of writing an entire extra step for this, I'm also going to make this 2 an exponent on my x plus 2 argument. So I end up with log base 3 of x plus 1 minus log base 3 of 2 minus log base 3 of 4 plus log base 3 of x plus 2 squared. And now I could rearrange these terms. I'll do that on this example just to show you how it works. I'll put all my positive logs first. So I'll have log base 3 of x plus 1 plus log base 3 of x plus 2 squared. And then I'll say minus log base 3 of 2 minus log base 3 of 4. And then I just start combining left to right. So all my coefficients are 1, so I can put my logs together. So I'll combine the first two logs into a single log, log base 3, and because this is addition, I'm going to multiply my arguments. So I have log base 3 of x plus 1 times x plus 2 squared. Then I'll copy my next two logs. Then I will move on to my next step and combine the first two logs. I have subtraction, so when I combine them, I'll divide in my argument. So on top I'll have x plus 1 times x plus 2 squared over the argument 2. I'll copy down my minus log base 3 of 4. And then finally, I'm down to just two logs that I'll combine. Since I'm subtracting, it'll be division again. Log base 3. If I divide this fraction by 4, it's the same thing as multiplying by 4 on the bottom. So I get x plus 1 times x plus 2 squared over 2 times 4, which is just 8. Right, I'll mention this off to the side in case I confused you. If I want to divide by 4, that's equivalent to multiplying by 1/4. So the 4 just multiplies on the bottom when you divide by 4. And now I put all my logs together into a single log. And there are two examples combining. Let's work in reverse and expand. So lots of ways to say this. I usually like to say expand completely, meaning use your log laws as far as you can to expand. Sometimes you might see into sums and differences of logs. But I will oftentimes just say expand completely. All right, number one, log base 2 of the argument 3 x to the fourth y to the fifth. And when we want to expand this, we can see we got multiplication and multiplication. 3 times x to the fourth times y to the fifth. So I'm going to go ahead and split all of those multiplications up with separate logs that are added. So log base 2 of 3 plus log base 2 of x to the fourth plus log base 2 of y to the fifth. And then I look at each of the logarithms and ask, can they be expanded further? Log base 2 of 3, there's nothing going on in the argument, so we can't expand. But log base 2 of x to the fourth, I have exponentiation here, which I know can turn into a coefficient. And the same thing with the exponent of 5 on my argument turns into a coefficient. So I end up with log base 2 of 3 plus 4 times log base 2 of x plus 5 times log base 2 of y. Then I look at my arguments again, 3, x, and y. I don't have any operations in my arguments, so I know I cannot expand any further. So that one's not too bad. Let's try another one. Expand log of the fraction 5a over 4b squared. Well, this guy is division. So I need to take log of the top minus log of the bottom. So I've got log of 5a minus log of 4b squared. Then I look at each log at their arguments and ask, are there any operations that I can expand further? And I see that they both do. They both have multiplication, 5 times a, 4 times b squared. So I need to split log of 5a into two logs. So log of 5, log of a, and because this was multiplication, I'll add those logs. Minus, and then I need to do the same thing here, log of 4. Since this is multiplication, I need to add log of b squared. Now here's a place where a lot of students mess up. I'm subtracting log of 4b squared, and log of 4b squared is all of this. Well, because I have this plus now, I can't write it like the way I have now because all I'm doing is subtracting log of 4. I'm not subtracting all of it. So to subtract all of it, we have to put it in parentheses. So I'll put an asterisk next to that because that's important. Okay, now we look at our arguments again and ask, can we go further? I can't do anything with 5 or a or 4. There's no operations. But I do have b squared, so I can make my exponent a coefficient. And I can get rid of these parentheses by distributing my negative. So we get log of 5 plus log of a minus log of 4 minus 2 log of b. And now we can do nothing further with those arguments. Hope you're getting the hang of this. It's one little step at a time, working on each individual little operation. When you try to rush this is when you'll mess up the notation and get really confused. So take your time as you work through these. We'll do one final example of expanding. Example 3, let's work with a natural log of the cube root of 5x squared. Now, you may look at this and think multiplication, but the problem is the multiplication is buried within a cube root, so you can't deal with that yet. You need to deal with the root first. Well, you may recall that a cube root is the same thing as raising what's inside to the 1/3 power, just like a square root is a 1/2 power. And now when we look at our argument, I've got something raised to a power, so I can take this power and make it a coefficient first. So I get 1/3 times the natural log of 5x squared. Now I'm looking at my argument, 5x squared, and I've got multiplication, so I can split that. But notice 1/3 is multiplied by this natural log, and this natural log is going to split. So I need to multiply 1/3 by the result of this. So I have to put in parentheses or brackets. We'll use parentheses. Students get confused sometimes when I use parentheses or brackets. It doesn't matter which one you use. Okay, so natural log of 5 plus, right, becomes 2 logs, and addition because we had multiplication. So natural log of 5 plus natural log of x squared. And last, I can just make this exponent a coefficient. And if I want, I can distribute my 1/3 to both. So I get 1/3 natural log of 5 plus, this becomes 2 natural log of x, but when I multiply by 1/3, I get 2/3 natural log of x. And now we can't do anything further with those arguments. Okay, logarithm laws, there's a lot going on here. Get plenty of practice. You can get really good at these, and they'll be handy not only for this class now, but when we solve equations, when we look at inverse functions later, lots of different applications here, but also they're really handy when you get to the calculus courses. You'll use these log laws all the time.